So during this Olympus gas well, we also know that, of course, we're producing some gas. And you'll see in this screen that composition of this gas has been given to us. Okay, so we will do this. This is what we will create now. We will add a gas analysis in our study. Okay, so the next step here is go to the Actions pane and add a gas analysis. Double click on it, and then let's change this name. Rather than say just gas, just name it Olympus gas. Okay. So this gas to the left, to the right, you'll see that it goes, it's just basic hydrocarbons. You can see here that these are all alkanes, and it goes up to hexane. Okay. The software is selecting methane as the makeup ion, or not makeup ion, as the makeup molecule or as the makeup gas for this specific analysis. So whenever you enter composition, and if it doesn't add up to 100%, the software will add methane to complete that 100% mole percent of the gas composition. So let's start entering the gas composition that was measured at the separator. So this is the first is it was measured, the composition of water was measured or was given, and that was 1.8 mole percent. Let me just put this. Then we have nitrogen, a little bit of nitrogen, 3%.
Can you just explain why are we doing this gas composition? What are we trying to accomplish with this?
Yes, so this is a gas well, and we are trying to accomplish that we are doing the mass balance. We need this mass balance. We need to account for the production rate of gas. We need to account for the production or the produced brine, the production amount of brine. And we need to account for the vapor liquid equilibrium. So whenever you have a gas, and in this case, this gas has, you'll see that in the composition, you'll have CO2 and H2S. These gases will partition into this water phase, and that will have an impact in the scaling tendencies. So if you are given a gas analysis, it's important that you know the composition so that you are actually accounting for the risk, scaling risk during production.
So, but wouldn't the H2S analysis be included in the liquid phase? So why do we, and that you're saying is because the pressure is changing, and so there is a vapor liquid equilibrium that's changing.
Correct. Mm-hmm.
Okay.
Yeah, and we want to account for all of that. So if temperature and pressure is changing, what happens to the composition? What happens to the partitioning of CO2, H2S? And that has an impact also in the composition of the brine, and that will lead a decrease in pH, for example. And that decrease in pH increases corrosion rates, things like that. Or it could decrease the scaling risk. We don't know, and that's what we are going to study here. Okay. So we have this gas. This gas was also found that had 1.5 CO2 composition. It had some H2S, 0.5. Methane, it had 65%. Ethane, 14. 8 for the propane. Isobutane is 1. And butane is 3. Isopentane, 0.5. Normal pentane is 0.7. And hexane is 0.5. Perfect. Now I want you to notice something. I was saying that methane was being the gas used to normalize this gas. And sure enough, we needed 0.5 mole percent to complete the 100% here. So we weren't given exactly 100%, it was 99.5, and the software added methane to complete that 100%. Okay, let's save. The next step is to calculate the properties of this gas, just as we did it with the brine. So we go to the reconcile, and in here,
how do you save it?
Here, in the save icon. So then we calculate the properties of this. These are by default the stock gas conditions. So it's 15 degrees C and 1 bar. And then we go ahead and calculate. Again, we just want to make sure that we actually have gas here. Sometimes people have entered some composition here and they end up having oil or something like that. So we just want to make sure that we have a gas here, a gas phase. So in the summary table, in the summary part, you'll see that the software is saying that we have a little bit of liquid. We are condensating a little bit of liquid. And what happens is that the software is saying that really this gas can hold 1.75 mole % of water, and we enter 1.8. Okay, so there is maybe was an error in measurement. It's just within uncertainty, right? Measurements. And then you have 99.95% of 99.95 moles of vapor phase. From the liquid part that you created, it was a little tiny bit that condensed. The pH of that water is 4.75. Why? Because you have CO2, you have H2S that will contribute to the acidity of this water. Okay, but this is mostly a gas. Now we're going to put this gas in equilibrium with the brine, okay, and see what happens to the scaling tendencies. So we are going to go to the Olympus production, click on Olympus production, click on design in the design tab, and let's go back to the inlets sub-tab here. So initially we had the brine, now we want the gas. We want to add the gas, to mix these two together. So we select gas, and under name, the software recognizes that we have an Olympus gas. And we enter and we select the gas. It was given to us, it was measured that at separator conditions, they operators measure, how much was it, 250 standard 1,000 cubic meters a day. So that's the amount of gas that we're going to enter here, 250 standard 1,000 cubic meters a day. Okay, so nothing else changes here. So we go to conditions again. We have already entered this production or this 250.
Okay.
And conditions, we don't have to change anything here. Everything remains the same. For solids, make sure that you select the standard solids and then go ahead and calculate. Okay. And the software, this will answer your question. I don't know if I am getting your name right, but Radisaf?
Yes.
Okay, Radisaf. So this will answer your question here. So if we go to the plot, let's see the default plot first. So in here, now we are going to see what happened to the scaling tendencies, right? Before, only with the water, we were predicting that we had supersaturation of calcite, 15 times above, since 15 times supersaturated. By putting this gas in equilibrium with the water and at different temperatures and pressures, now you can see that at all times calcite is not even supersaturated. It's undersaturated or subsaturated, and what now is precipitating out only is the barite. Okay.
Okay.
So here is when you start asking yourself, what could have happened? So maybe the CO2 and the H2S decrease pH. The calcite is very sensitive to the pH changes. Barite is also sensitive to changes in temperature, so that's why maybe it didn't really change very much if you compare it to the original only brine. If you had only the brine, you'll see that probably they are more or less the same scaling tendency values. But the calcite definitely had an impact on this supersaturation, on these pre-scaling tendency values, because now we are equilibrating, or we are taking into account that gas phase that we measure at the production, at the separator. Okay, so that is the gas. Now,